In this chapter, I just want to go over some of the things that you would have to consider as an analytical chemist if you were asked to choose a particular method for a particular analysis. Okay, so as an analytical chemist, that might be something that you will do. So you would have to be familiar with some of the different criteria that are specific to different methods, and then using all that information, decide which method is the best for a given problem. So here are just some of the considerations that you would have to think about when selecting an analytical method. Some of them you're familiar with, like accuracy and precision, but we'll go over them briefly again anyway. Sensitivity we'll go over a little bit more when we talk about calibration curves, and then the rest I will talk about in the coming slides. So accuracy is just simply how close is your result to the actual value or the true value. Now, a lot of times you won't know what that true value is because you'll be analyzing an environmental sample or some real sample where you don't know what the actual number is. You'll be asked to find what the actual number is. But in the case that you do know what the true answer is, you can determine how accurate your analysis is. And when we get into the statistics chapter, we'll talk about how we can be confident in our answer even if we don't know what the true answer is. So if you know what the answer is supposed to be, so for example in lab there is one experiment where you will be given the amount of iron in your sample because you'll be doing an analysis of an iron tablet, and the iron tablet is from some iron vitamins, so you can just look on the bottle to see what is supposed to be there. So you can determine how accurate your result is just by using the equation on this slide. Okay, so if you wanted to figure out your percent accuracy or your percent error in this case, you would take your measured result, subtract what you expect it to be, or the actual result, the one that's printed on the bottle, divided by the expected result, multiplied by 100, and that will give you your percent difference from the actual value. Now, precision is how reproducible your measurements are. So if you were to measure the same sample 3, 4, 5, 6 times, you would be trying to figure out how close each of those measurements are. Now, it's the same sample, so its concentration isn't actually changing, but the concentrations you determine from your analysis may or may not be very similar. So for example, when you're doing the titrations that you've done in lab or will be doing in lab, the concentration of sodium hydroxide, for example, is not changing. And each time you do the analysis, you would expect to get the same amount or the same concentration of sodium hydroxide, but it may or may not be the same depending on how well you perform the titration. So how precise are your results? That's going to be a measurement of your variability. So how variable are the results of an analysis done several times? How repeatable is it? Now, the thing I need you to know is that precision does not imply accuracy. So you can be very precise with your results. You can have an amount of KHP in your unknown, 38.56, 38.54, 38.50%, for example. Very precise, all the answers are very close together, but that does not mean that you're accurate. There could be some error that occurred throughout the experiment that you just kept doing over and over and over again that resulted in your reproducibility being just fine, but your accuracy being poor. So precision does not imply accuracy. So sensitivity is the ability of a method to distinguish the difference between samples of different amounts of analytes. More specifically, a sensitive method will be one that is able to distinguish the concentrations of samples that are very closely the same. So very small differences in a concentration between two different samples will be able to be distinguished by a method that's sensitive. A method that is not sensitive will see those two samples as being the same concentration. Okay, so higher sensitivity, ability to distinguish small differences in amounts of analyte. Selectivity and specificity have to do with the method being able to only measure the compound that you are interested in. So a lot of samples that would be done in a real world situation are going to be complex. A sewage water sample, a blood sample, right? So these are not samples that are clean. It's not just water and one other thing in it. It's a whole bunch of proteins, for example, in blood. So if your method is supposed to only measure one particular protein, you want to make sure that that method is selective or specific to that particular protein. So blood, for example, has hundreds of thousands of different proteins in it. If your method can only measure one of those proteins, the one that you're interested in, you could say that's a very selective method. Something that's not very selective might be able to measure a number of different proteins that are very similar. So the answer that you get at the end, the result you get at the end, is not going to be indicative of a single protein. It would be indicative of, for example, a family of proteins. And the components of a sample that are measured, even if you're not really wanting to measure them, are called interferences. So these are things that are interfering with your analysis. They're giving a signal. They're saying that your analyte is there at a specific concentration, or adding to it, right? Saying there's more than there actually is, because your method is measuring more than one protein, for example. So that's interfering with your analysis. It's called an interference. A robust method is a method that is relatively free from these interferences. Okay, so one that can be used on a wide variety of matrices. A sample matrix is simply where your sample is located, or what it's located in. So if you have a water sample and you're looking for nickel, then the water sample, all the organic material, nutrients, or whatever else might be in there is the sample matrix, and the nickel is your analyte. If you have a blood sample, the blood's going to be the matrix, and your analyte would be the protein or amino acid or whatever else you need to measure within the blood. Okay, so a robust method is going to be able to deal with those different types of matrices. A rugged method is one that is unaffected by small changes in experimental procedures or conditions. So some methods are very picky in how they work. So if I were to do an analysis using one method, and then you were to do an analysis with the same method using the same recipe, the same procedure, we might end up getting different results just because we do something slightly differently. So that would be a method that is not very rugged. Okay, small changes are going to affect the result at the end. So a method that is rugged, different people can do it, have small changes in the way they do the procedure. There could be small environmental changes, and that's not going to affect the result at the end. Another thing you have to consider is the scale of the operation. How much sample do you need, and how much sample is available? If you're looking at a lake water sample, there's definitely going to be a ton of sample that you can use, so you're not going to be limited by how much you can remove from the lake. Whereas if you have a blood sample or a urine sample or something similar, there's only going to be so much sample available, so you're going to have to deal with being able to use less of that sample. What are we expecting the concentration to be? Is it expected to be a high concentration or a low concentration? And the method that we choose is going to have to be able to give us a signal. So what is the minimum amount of analyte that we need to give us a signal? So we may need a method that can measure small concentrations, or we may need a method that can better deal with larger concentrations. So another consideration, what type of equipment are we going to be needing to do the analysis? Do we need something that's expensive, some instrumentation, something that can separate a mixture, something that can measure the masses of molecules like mass spectrometry? Or is this something we can do on the bench? So something we can do with a titration type analysis, something that is relatively cheap. We also have to consider how much time is this method going to take, because time is, of course, money. And we have to consider the method from start to end. So the starting part of the method would be taking the sample. Where do we have to go to take the sample? How long is it going to take to get that sample? Do we have to prepare that sample in some way? Do we have to filter it? Do we have to extract something from it? Do we have to freeze dry it? Do we have to homogenize it? Okay, so what has to be done to that sample in order to make it ready for the analysis? And then, of course, how long is the analysis going to take? A lot of instrumentation that's available these days can be automated, so that just means that You can set up the procedure for the instrument in the computer, load up the samples, set it to go, and then you can walk away and do whatever else you need to do. So that's obviously going to be more time efficient than something that's not automated. Now, something that's automated is going to cost a lot more than something that isn't. So some of the equipment that's used in an analysis might be expensive. Some of the reagents might be expensive. For example, you may need to have very pure reagents to do the analysis because you're looking at small concentrations of your analyte. The more pure the reagent, the more expensive it's going to be. And maybe the equipment that you're using requires very specialized personnel or people that know what they're doing, people that know how to use the instrumentation. And they're probably going to cost a bit more to employ than those that maybe have more general lab skills. And how fast can each of these samples be analyzed? Is it something that's going to take minutes? Is it something that's going to take hours? Right? How long is that going to take? So instrumental methods are usually more costly, but they do have some benefits over bench type methods. Okay, they're good for separating mixtures, they're good for detecting low concentrations of the analyte, but that's going to up the cost and the expertise and a bunch of these other criteria. Okay, so your final decision is going to depend on these criteria, but you're not necessarily going to have the best of each of these criteria. There may only be one of these criteria that's going to drive your decision in a specific direction. For example, if you definitely know that you need to be able to measure small concentrations of analyte because you're expecting very small concentrations, right, in an environmental sample, then that might direct you to a method or a very specific method that may be very costly. It may take a lot of time to do, but you might be bound by one specific criteria which will limit what you can actually choose. So if we had a situation where we wanted to determine the status of an environmental system or assess the long-term trends in the health of a system. So for example, if we're looking at some pollutant in the Detroit River, we want to know how it's changing over time, and that time could be months, it could be a season, it could be years, it could be decades. We may have to go into previous results that have been published years ago, or maybe we're just starting something today and need to continue on our research for a specified amount of time. So if you want to know how these concentrations of pollutants or nutrients are changing over time, we're going to have to choose a specific method. We don't necessarily just need to know about our system, so we might not be able to just limit ourselves to what's happening in the Detroit River. We might also need to know about how that affects other things in the region, right? The animals, habitats, towns, cities, other lakes and rivers that the Detroit River is either connected to or drains into. Okay, and the Detroit River is a drinking water source, so how is our monitoring system, or how are these changes that we are monitoring affecting drinking water and all of these other systems? So when we choose an analytical method for this type of problem, we have to make sure that the method that we choose is the correct method, because if we choose the wrong method, we're going to get useless information, and that just ends up being a waste of time and a waste of money, and the analysis would have to be done over again anyway. So we should try and get it right the first time. So for example, the Flint water crisis, where lead was found in the drinking water of those living in the city, what if the method that we chose to measure lead concentrations in drinking water was one that was not good enough to measure such low concentrations of lead? If that was the case, we choose the wrong method. It can't even measure the small amounts of lead. What the method would show is that there is no lead in the water, or at least the lead that is in the water is lower than what can be detected by the method. So what kind of information are we getting from that? Nothing useful, right? We need to know how much is there and how low that concentration is, because it doesn't take a lot of lead to have health effects on a population. So it's very important to choose the correct method. Otherwise, the information you get is not going to be useful at all. So that's it for this. I just wanted to give you an idea of some of the criteria that you may have to consider when choosing an analytical method. Right? If you continue on in chemistry and get employed as an analytical chemist, or in a field that requires some analytical chemistry knowledge, then this might be something that you will have to do in the future. So knowing about the different methods, knowing their pros and their cons, what they can and they can't do, may become important for you in your future. Now, you'll learn a little bit more about this in Chem 383 or 481 if you continue on there. That's when you learn more about the instrumentation and the advantages, disadvantages of each of them, and how you might choose one of those methods for a specific analysis.